All right, let's dive into a really incredible engineering challenge. We're about to go on a high-stakes heist, but what we're after isn't gold or diamonds. No, our target is a single drop of liquid, a perfect fluid sample. And if you mess this up, it could cost $1 billion.
See, miles beneath our feet, trapped under absolutely crushing pressure, there's this fluid that's basically a liquid treasure map. It holds all the secrets to an entire energy reservoir, what it's made of, how it'll behave, what it's really worth. This isn't just oil or gas, it's pure, unadulterated information. And here's the kicker. This prize is unbelievably fragile. The second you try to bring it up to the surface, the laws of physics themselves pretty much conspire to change it, to corrupt it, and to make it totally worthless. So this isn't just a heist. It's a mission against physics itself. So what is it that makes this prize so incredibly hard to capture? Well, to pull this whole thing off, we first have to understand the security system we're up against. And that means understanding the physics of the problem. This right here is our target. It's called a representative sample. And you should think of it as a perfect liquid fingerprint. It's a tiny bit of fluid that has to be completely 100% identical to how it exists deep in the earth, totally unaltered. Anything less than that isn't just a bad sample. It's basically a forgery. The huge problem is that the journey to the surface is, well, it's a battlefield. The very act of pulling the fluid out of the ground actually changes its fundamental properties. The environment itself is actively working against the engineers trying to get the sample. And this is the main security system, the pressure trap. See, deep down, all that immense pressure forces everything into one stable, pure liquid state. But as the fluid rises up toward the surface, that pressure starts to fall off. And that drop in pressure, that's the alarm. Suddenly, gas can bubble out of the oil, or liquid can literally condense out of the gas. And just like that, the perfect sample is contaminated, it's no longer representative. The trap has sprung. So these two terms you see here, bubble point and dew point, these are the critical thresholds. You can think of them as the laser tripwires for our heist. If the team lets the pressure drop below this exact point, the mission is toast. The fingerprint is smudged. Game over. So how do engineers actually disable this pressure trap before they go in for the grab? Well, you don't just rush a job like this. First, you have to prep the scene. You have to case the joint. They do this using a technique called well conditioning, and it's exactly like a crew casing the joint. For a good long while before they even think about taking the sample, they carefully manage the well's flow to flush out any of that corrupted two-phase fluid that's hanging around, and instead draw in the pure original stuff from way back in the reservoir. Okay, but you can't just look and see what's happening thousands of feet underground, right? So how on earth do they get the real-time intel? How do they know that the fluid is finally pure and it's actually ready for sampling? This is their mission dashboard. Their primary tool is the gas-oil ratio, or GOR. And you can think of it as the vital signs monitor for the reservoir. If that GOR reading is holding steady, totally constant, they know they're getting pure, single-phase fluid. That's a green light, a big go for the mission. But if it's dropping or if it's rising, that is a hard no-go. The sample would be corrupt, and the whole mission's a bust. And, just like any complex operation, some targets are just too risky. You have to know when to walk away. If a well is also producing water, for instance, or if it's using artificial methods like gas lift to get it to flow, the fluid is already too chaotic, too mixed up. The mission is aborted before it even gets started. Okay, so the well has been conditioned, the GOR is stable, the coast is clear. It's go time. It is time for the grab. And the team has two main techniques they can use, and each one is suited for a different kind of situation. Let's compare the two main methods. We can think of them as the solo job, which is a quick, direct snatch deep underground, and the team operation, which is a much more complex, coordinated capture that happens up at the surface. So the solo job, or bottom hole sampling, is all about speed and stealth. They send a special pressurized container way down the well on a wire, right into the heart of the reservoir. It pops open, traps a small, pristine sample, and seals itself shut before they bring it back up. It's the perfect approach, but only if the conditions are just right. The oil can't be too thick, and, this is crucial, the pressure has to stay above that critical bubble point the whole time. And then you've got the team operation, also known as surface sampling. Sometimes you just need a much bigger sample, or maybe the conditions downhole aren't right for the solo job. So here, the team actually lets the fluid separate into gas and liquid at the surface. They capture a sample of each one while precisely measuring how fast they're flowing. Then, later, in a lab, they use math to recombine them and perfectly recreate the original fluid. It's way more complex and requires absolute precision. So the engineers have outsmarted physics. They've conditioned the well. They've executed the grab. But why? Why go through all of this insane trouble? Why does one tiny little fluid sample matter so much?
Well, it's because of this number. A single bad sample, one smudged fingerprint, can lead to massive miscalculations about how to develop an entire energy field. You build the wrong equipment, you pick the wrong strategy, you make the wrong investment. The cost of that one mistake can easily spiral into the billions. I mean, everything hangs on the success of this mission. That one single pure sample provides the data that determines how billions of dollars of infrastructure are going to be built and how a massive natural resource is going to be managed for the next 20, 30, even 40 years. It's a truly microscopic mission with absolutely macroscopic consequences.
It really makes you wonder, doesn't it? This whole incredibly intricate operation is all about capturing data that is otherwise completely invisible. And it leaves us with a final question. What other crucial data, hidden in plain sight, will shape the future of our biggest industries?